Okay, so it's my pleasure to introduce our very first speaker, Bob Donley, and he will be speaking about methods of validation for Adinkra models in supersymmetry. And this is our first talk since COVID with the CUNY representation theory seminar. Every 2 weeks, we'll be having a talk from here on out. Yeah, Bob, thank you. It's all yours.
Great. So thanks for the introduction. Thanks for everyone showing up. If you're in New York, it's pretty dreary out there. So yeah, I guess first it's great to be back. It's what, 6 years now?
Yes.
5 years?
Yeah.
So methods of validation for Adinkra models of supersymmetry. I guess I'll start with acknowledgements. So this talk is really two short talks kind of fused together, but the fusion makes sense. The overall project, this is joint work with Jim Gates in Maryland. He's project leader. Tristan H, who's at Howard, and Rishi Nath, who is CUNY's own, here in the audience. Let's see. So this project overall was initiated with a grant from the adjunct program for SL Math, that's formerly MISRI or MSRI. Let's get that right. I think it's emissary properly if you're going to go with MSRI. And also acknowledge the second part of this was done on my fellowship leave at Institute for Advanced Studies. So I'm going to acknowledge that gratitude for that also. Okay, so the main theme of the talk, the first half of the talk really doesn't have a lot of representation theory until we get to the second half, and then things kick in and you kind of look backwards, and then all we're doing is wave space. So the first half of the talk is actually going to be about combinatorics of hypercubes, and the representation theory there is going to be weight spaces, which I really don't talk about at all. That shows up later. And there, the topic is Adinkras with an I. For the second part, that's where the real representation theory comes in. That's representations and finite dimensional representations of orthogonal groups. And then that's Adinkras with a Y. So the Y is to suggest, of course, we do representation theory, and we all know Dinkin, and so that's embedded in the Adinkra with a Y title. Okay, and this Adinkra with a Y is sort of where the frontier is, doing this combinatorics with representations. All right, so for the first half, Adinkras with an I. Table of contents, as noted, this is joint work with Gates, Hoops, and Nath. And the first preprint of the project's up on the archive, and that there, I'm not really going to do the new results out of there, which are about magic squares and Latin rectangles, but it's a good way to get us started on a good introduction, which I need to do Adinkras with a Y. All right, so where things begin. Okay, so we have a physical model. I'm not going to say too much about the physics because I'm not a physicist. And as far as the project goes, I did not come through this through a physics education. I was just basically dropped into it and started solving some problems. So I'll do my best with this. But for specific questions about physics or supersymmetry, maybe we could farm to Jim in the chat. All right, so the model I want to start with. So I want to talk about supersymmetry. So what happens in supersymmetry, we're going to have particles. We have bosons and fermions. We'll think of those as being functions of time, could be complex or real valued. On these functions, we're going to have operators that we call supercharges. So they're just going to be linear differential operators. And we're going to want relations among the supercharges. And so you'll note these look very close to the things we do at Clifford algebras. Clifford algebras are part of the story, but not really much of what I'm going to talk about today. We're going to go in the direction of combinatorics. Now, for the example I have on the board, the way I want the supercharges to act, we'll have, so the point of supersymmetry, what makes it supersymmetry is this exchange of bosons and fermions. The way that I have it in this example, you'll notice in this exchange of bosons and fermions. If I ignore the complex numbers or the differential operator parts, all this is you could think of as being vertices, and then we're just doing exchanges of vertices. And that's where the combinatorics comes in. So here you've got some indexing that if the B's and F's are vertices, then we've got very specific movements going on here.
Are these fields, does it matter where these fields take their values in?
For purposes of this, it doesn't. We're just trying to set up a combinatorial model. So they're just, you can think of them as just being one-dimensional vector spaces, really is what's going on here. Okay, to make this a little bit more representation theoretic, you could break these out into matrices. That's what we do with representations. We turn abstract things into matrices. Here, the Q's are actually going to generate an algebra. I think it's the extended Poincare algebra. And then by choosing these matrices, you're getting a representation of that algebra. So that's what's going on here. And then you note if we drop the differential operators of the i's, we get signed or regular permutation matrices. And that becomes a big part of the theory, but maybe, well, it's in the background of things I'll do today. Okay, and so if I take the model I just had on the board, we could convert it to a graph as follows. And what I want to do with the graph is, so we have the bosons and fermions. I want to indicate the supercharges by just drawing, if I apply supercharge, I want to link the boson fermion exchanges with colored edges. And so for Q1, we'll put in blue edges. If I use red for Q2, then you'll notice, since we have the squaring, gets us back to the identity, technically, if we ignore a lot of complex numbers and differential operators, then we get a square with alternating colors. The key parts here for supersymmetry, we'll have a bipartition on the vertices, the bosons and fermions. The supercharges give us bijections between these sets. And then the graph theory, the word we want is a perfect matching. And I'll do that precisely in a few slides. Okay, and that's the most basic model for supersymmetry. Now, for an Adinkra, we want to take this model and blow it up to bigger things. The things that Adinkra is going to need. So there's going to be 4 parts of the definition. We have one factorization, which I'll get into these. So one factorization, special one factorization is going to need the quadrilateral property. And then once you have the quadrilateral property, we want it to admit a totally odd dashing. And then after that, we want to put a partial ordering on this graph. So these are just examples of what's going on. We'll do more specifics moving forward. All right. Let's define some of the things precisely. So the perfect matching, if I have a graph, perfect matching is just going to be a subset of disjoint edges that meet every vertex. So the idea with a perfect matching is exactly what it says. I want to take all the vertices and put each vertex with one other vertex. Also called a one factor. If my graph decomposes into disjoint one factors, then that's what we call a perfect matching. Now, to express that, a convenient way to express that if you want to draw pictures is going to be, well, what I can do is for each one factor, I can assign color to it, and then that's going to give us what we call regular edge coloring. And so regular edge coloring is just going to be a graph where we've got colored edges, and at each vertex, we have an edge of one of the colors exactly once. So I'm going to go a little bit through the zoo on just to give you a feel for each kind of part of the definition before we get to Adinkras. So kind of the canonical example for one factorizations, or the one that gets studied the most actually, is going to be the complete graphs of even order. So there's going to be kind of canonical ways to color a complete graph of even order. I'm not going to do that here, but as an example of a one factorization, if you notice, we've got 5 colors, and at each vertex, we have each color shown up exactly once. I could also break this out so you can see the perfect matchings clearly too, although here I'm only showing 3 of them. Right, perfect matching, of course, requires an even number of vertices, so it's got to be a complete graph on even order. Now, so trying to go general, well, what kind of things, what would you need a graph to have these one factorizations in general? Well, as a corollary to Hall's marriage theorem, for a finite graph, it's enough if I have k regular graph, so just we have k edges at each vertex, it's enough to just have bipartite to have a one factorization. And that's kind of a standard result in the theory. Okay, bipartite, remember, we're just taking a partition of the vertex set. To be bipartite would mean we can only have edges that join one part of the bipartition to the other part. And then it'll be helpful to note in examples coming up, so if you're trying to hang in there, in the examples, if you want to check for bipartite, you look and see if you have odd cycles or not. So that'll be a quick check. So for instance, here we see right away, if I'm thinking of Platonic solids, if I want to go through the bipartite and regular condition, well, we got odd on the tetrahedron. We'll actually have odd cycles on all of them except for the cube. And it's going to turn out the cube is actually not just the example here, but it turns out to be a big example for everything. It's the example for Adinkras. Okay, and so one factorizations as noted for the Platonic solids, we have the cube, hypercubes in general will have this. And then, so I cut a slide, but if you do the, above the Platonic solids, you have the Archimedean solids. So they're kind of interesting to play around with. And then you get those truncated octahedrons, actually important for many things in the Adinkra game. The Platonic solids all admit one factorizations, even though they're not bipartite. So Hall's marriage theorem might not apply, but you still can get a one factorization if you start putting pen to paper. They're not too hard to find. And then other places to find one factorizations, of course, you can just go and look at one skeletons of the interesting polytopes that you have in combinatorics. Okay. So that's one factorizations, give a little overview and feeling for that. Then we want this, this quadrilateral property. So let's go back to the idea of what's happening with supersymmetry. What I can do with a graph that has a regular edge coloring, well, somebody calls color, I think it was like square dancing or something. You call color, and then things on the ends of that colored edge have to exchange places. So what we have is our permutations going on, but not just permutations, they're very special. They have to be order 2, and they have no fixed points. So that I can generate a group off of that, and I can study what that group does. And so for examples here, so here's some regular edge colorings with the different generators for those involutions. And actually, it's kind of tough trying to figure out what groups come out of that. So I can only do that in small examples if it's not an Adinkra case. Okay. Now, we're dealing with involutions. So since it's a representation theory seminar, the first thing that comes to mind dealing with involutions are Coxeter groups, because they're generated by involutions. Not so interested in Coxeter groups for what follows, although again, it's an important part of the Adinkra game. But if I have a general group, if I come across just a random group out in the wild, one of the first things I should check is, you check the group properties, and always property number 5 is it abelian or not. So this abelian property is going to be pretty much what this 4-color property is. If my group that comes out of the involutions is abelian, you're going to have the 4-color property. And so what happens here, what happened on the board, if you have involution and abelian, well, the abelian property, if you push it to one side, you're going to have this alternation of involutions, which is the same as running around a square. And then that's running around what we call a bicolor 4-cycle. And so the quadrilateral property, without any of the group theory language, what it says is if I take our graph and I restrict to any 2 colors, what has to come out of that has to be a disjoint set of cycles. We want disjoint set of 4 cycles. And so that's going to be the next ingredient for the Adynkra. And so an example here, this is the 3 cube. I'll talk about the special coloring for hypercubes. Hypercubes always have a canonical edge coloring. And you can see here that this thing, when I restrict, it breaks up into the disjoint 4 cycles as promised. Okay, and then that's pretty much the statement. And so the thing is, if you think about involutions and abelian and finite, you're looking at a product of Z2s. Product of Z2s, if you think about things that relate to that, well, you got binary codes, and then binary codes might make you start thinking about cubes. And so it's going to turn out, if our graph is connected, it's a one factorization with a quadrilateral property, then it's going to turn out to be a quotient of a hypercube. And by quotient, we got to talk a little bit about that, although I won't say too much, what it means to take a quotient of a cube when you have a coloring. But there's a way to do that all consistently. Okay, so cubes. Okay, so what do we want to do with cubes? Of course, for cubes, we could talk about with the Boolean lattice, so the poset of all subsets of a set. But it's really useful to go over to binary codes. So we have that already there naturally from the products of Z2s. And so I could start building these posets in the natural way with binary codes. We start at 0, and then you just go up the poset, the Hasse diagram, by just adding 1s where you can. And then that's going to track out a cube if you use the Hamming distance to put lengths in. So cubes are going to be fundamental to everything that we do. So we'll come back to this. Now, for hypercubes in general, so we construct a hypercube. To color it, there's a lot of ways you can color a cube, but the one you want that's going to be compatible with binary codes is to do this parallel edge coloring. And what that just means is, for instance, for the square, it's exactly what it says. You color parallel lines with the same colors. For the 3 cube, the same idea. And then there's a generalization of that for hypercubes, which would be you join the you'll assign a color to a coordinate, and then the vertices that differ everywhere but in that coordinate, that are the same everywhere but in that coordinate, we would want to put an edge of that coordinate's color. And so that gives you a natural edge coloring of any hypercube. The quadrilateral property is straightforward, just an induction proof. And then for cubes, of course, we get the Z2 for this involution, the group generated by involutions from before. Great. For connected one factorizations that are not cubes, well, we could take the 3 cube and connect the diagonals. That's going to have 4-color property. And right, so that has the 4-color property, but that's not going to be a cube just by counting edges and comparing with vertices. So if that was a cube, it would have to have, if it's 4 regular, then it's got to be the 4 cube. But if it's the 4 cube, it doesn't have the right number of edges. So that's not a cube. And it'll turn out that's the story. Pretty much, if you want the quadrilateral property and you're connected, you've got to be a quotient of a cube. Okay. Next, we have the definition of the Adinkra. We already have the 2 parts under control. So what I'm going to have to go back to next to get the last 2, we're going to need to revisit the physics to explain a little bit of how we put signs into things. I'll note Adinkras. So the Adinkra concept, so discovered by Fox and Gates, it's not like an old concept. It's 2005, so this is only 20 years old. And it's actually extremely developed. And what I'll get to in the first half of this is just telling you what the big punchline is for their work. Should note, so one thing about this Adinkra technology is that it's very much a physics thing. It really hasn't broken out into combinatorics. And so there's been an effort to try to expose more representation theories and combinatorics to it, because there's really a lot of low-hanging fruit for the taking, most likely, or at least I've been very lucky in finding things like the problem is not so much problems are difficult, but of course, since it's math, the hardest problem is coming up with the questions in the first place. So there's a lot of things that are just sitting there waiting. So that's an advertisement. All right. Let's see what we got. So I want to go to totally odd dashing. So I want to revisit the squares again. We have our supercharges Q1 and Q2. We have squaring a Q has got to get us back to the identity, which leaves open the option for putting negative signs when we do our switches. So if I want to do that, though, that's going to mean if I send a boson to a fixed fermion with a negative, it's got to be a negative when it comes back also. And so because we're going to join those two with an edge anyway, I can indicate on that edge that there's going to be a negative when we do the switch. And the way to do that is not to put in plus or minus ones, because things are already going to get cluttered when you start blowing up the bigger things. You want to put in dashes. And so that's what we have over here. The link between the B1 and the F2, which are picking up the negatives, are going to get the dashed edge. And so putting in these dashes on top of the one factorization, that's the next feature for the Adinkra. Okay. But that's not all, because not only do we have the squaring property, we also want an anti-commuting property to happen. And to make that happen, you have to have an odd number of dashed edges in any bicolor 4 cycle. And then that's what we call the totally odd dashing. Okay, there's also a partial order. The partial order, pretty much, we can always guarantee this partial order, and you can put arrows in if you're not going to use a Hasse diagram, which gives you the sense of the direction for the ordering. Not really going to say too much about this, but it's the fourth part. Now, the punchline here, so for these Adinkra graphs, it turns out that up to the totally odd dashing, there's a complete classification of these, completely in terms of binary codes. So let's review some of the terminology there. So what do we have? I want to have binary words. They'll all have length n based on the hypercube that we're using. Okay, we know that's a vector space over Z2. And then definitions, we have the weight of a word is the sum of the ones in there. We have even words, and it's going to be important for Adinkras doubly even. Why they wouldn't call, I mean, I guess you need some way to say multiple of 4, but they call it doubly even, as if your word is 4 times an integer. Let's see. So that's words. For a code, we're just going to have a subset of binary words, in this case, all of length n. And then the code's even if all the words are even, doubly even if all the words are doubly even. And then linear if it's a subspace in our vector space. To check these, typically you don't want to list all the codes, you just want to list the basis if it's a subspace. So you'll have an even code if you pick a basis. It's even if every basis element's even. For doubly even, you would need every basis element to have order 4, but you also need the bitwise and to be even. So it's not enough just to have multiple of 4. You got to make sure when you add things, there's still multiple of 4 also. And the bitwise and does that. For examples, okay, so for the 3 cube with the diagonals in there, the code that goes with that is going to be the all zeros, all ones. And then we'll have a D family, which is just take your 4 ones, shift by 2s until you run out of space in your length. That's a family. And then so these double even codes are classified up to length 28, and that's actually work of the Adinkra group. So that's something I would have thought combinatorics would have done, but it's physics. And of course, we have the E7 here, which also is related to the E7 from representation theory.
Repeat the definition of doubly even.
So doubly even code just means every word in the code, every code word has its weight a multiple of 4. So double even is 2 times 2. Well, so what I'm doing here, maybe I'm not explaining this well. The rows here are going to be the basis elements. And so if you add any 2 basis elements together, you'll see the multiple 4 property is not going to disappear. And probably see it. Well, I don't have it. Do I have it so that we, I don't think any of these get up to 8 because I don't have it long enough. So, but you see if you add any 2 together with binary addition, it's always 4 ones. All right. So, right. So, and like I said, the doubly even codes are classified, and there'll be a reference for that in a couple pages.
Classification.
Oh, I'm going to state that. That's the big theorem. It's not my result, but that's the big result for the first half of the talk. So like a review. So if your code's linear, what do the different properties give you in terms of the graph theory? If you have an even code, that's going to give you bipartite on the graph. Actually, I probably should note, right, the connection between the code and the graph, I'm skipping over that, but the idea would be is you have a natural, you take a hypercube and you think of that being associated to the group Z2 to a power. You have a code, and then you're going to take a quotient, which would be like gluing all the vertices together that glue together by the code. And then the edges, since this is done in a very particular way, it's going to preserve edges when you quotient with their colors. And so this is all stuff you just go and you check and it all works out. So with that quotient property, what comes out on the graph side of things, if your code was even, you'll get the bipartite condition. I think here I got to say connected for everything too. If you don't have any code words of length 1 or 2, code word of length 1, that's going to give me a loop. Code word of length 2 is going to give me a double edge. And then pretty much if there are none of those, you automatically pick up the quadrilateral property. And really, you're picking that up from the cube you're starting. And then doubly even is going to give us the possibility of a totally odd dashing. So it doesn't give you the totally odd dashing, it just says that one is going to exist somehow. And that actually is a result. All right. Okay, and then the big result, or I guess there's of course many results there, but this is the one that's very striking and the one that combinatorics should take note of. All right, so for an Adinkra, you have a chromatopology, which is really just letting go of like basically chromatopology would just be you have an Adinkra, you want to let go of the partial order and the totally odd dashing. You still want the possibility of a totally odd dashing on the graph, but we don't want the specific totally odd dashing. So what that means is if I have a connected Adinkra, then its chromatopology is given exactly by a doubly even code and vice versa. And so this construction coming out of supersymmetry is pretty much completely characterized using this business of code words. All right, and so that's the big result for first half. And then that's the work of, so if you do this, we've got a bunch of acronyms to refer to papers. So this one is DF Gill for the authors that are on it. Okay, so as noted, this is not just combinatorics. There's a whole constellation of subjects that feed into the Adinkra paradigm. Of course, sign permutation matrices show up, Clifford algebras show up. An area of very active interest now is geometrization. So that's Riemann surfaces. Spin is in the background here. This business of a cube, hypercubes are really kind of like graph-theoretic stand-in for spin representations. And then there's also sociohedra and cluster algebras and many other things. So this is not just a combinatorics thing. It actually pulls in from a lot of different areas. All right, let's see. For mathematicians, to get into the Adinkra with an I game, these 4 papers are recommended. They're not written. They're not totally devoid or separated from the physics, but they're written with mathematicians in mind for easier reading, a little bit more direct language for mathematicians. And then the Adinkra itself, so it's probably not a word you would normally, probably haven't heard the word Adinkra out of the math context before. So this comes from West Africa, Ghana, and these are ceremonial symbols. And so these are what proper Adinkras look like, or non-mathematical, let's call them non-mathematical Adinkras. And so it's definitely hearkening to something that's in the real world. All right, so that's the first half. That's the combinatorics. That's the overview of these graphical objects in supersymmetry used for solving differential equations. The newer material, so this is the project I've been working on for the last year, Adinkras with a Y. So Adinkras with a Y. Okay, so the preprint for this isn't ready yet. It actually, the project itself takes up 4 Excel workbooks. The interesting feature, well, the thing that's interesting to me about this project, aside from the math, so kind of being dropped into physics, it's sort of like representation theory. I kind of know what I'm getting into. With the physics, it kind of pulls from areas that, like I woke up in the morning, I have no idea what I'm going to be using by the end of the day. And for this project, it actually goes, like, the reason I can do this project is because I spent 3.5 years as an actuary, and I spent a lot of time in spreadsheets and knowing my way around how to deal with data, how to work with tables, and not just tables. Like this project, by the end of it, one piece of it has about 200 tables that you have to put together, and like it's a real data science project. Okay, so let's get into this. All right, so again, supersymmetry, there's a very concrete connection to the first half of the talk. What the Adinkra with a Y model, you could say a little bit more about what's going on with the physics in that what we're interested in supersymmetry is superfields. And so these are going to be functions that have both commuting and non-commuting variables. You want to get a handle of the non-commuting variables, which is coming from both spin and exterior algebras. And so what we're doing with Adinkras with a Y is setting up graph theory so that we can get a better understanding of the particulars in there. And you'll see that things really need some sort of outer theory to bring things under control. The numbers really kind of get out of control fast. All right, so that's the physics. What this means for mathematicians, and which is why I can do it, is that the problem itself is just we're doing irreducible representations of orthogonal groups. And the particular one is I'm going to take a spin representation or a sum of 2 spin representations, form the exterior algebra, and then we're just going to decompose that into irreducible. So that's the problem. So for representation theorists, that's pretty direct, and you got your different methods for how do you do such a thing. Okay, and so here's the connection to the first half of the talk. What happens is, so I'm going to talk about Adinkras with a Y, which is the object on the left. The nodes on the object on the left are going to be irreducibles of SO4. And at the bottom, the 0, 0 is a trivial rep. And I'll talk more about what's going on here. The labels are the highest weights. And what happens is, so we've got irreducible representations for the nodes on the left. We just restrict down to, say, the Cartan subalgebra to the weight spaces, and then everything is going to open up into an Adinkra. And here I haven't put any of the coloring or dashes or things, but the idea is to suggest somehow I think of Adinkras with a Y as being chunky, and you're just kind of opening everything up with a restriction.
So this graph on the left is restrictions to Cartan.
No, so the idea is on the left, those are irreducibles. Yeah. So each node's an irreducible. Once I restrict the Cartan, it's going to go from, say, a 4-dimensional thing to 4 one-dimensional things. So when I go to the right, I'm going to get much more nodes.
And what are the edges? Do you get the edges on the graph anymore?
Yeah, we'll talk about that. Yeah, so one thing I didn't do a good job with in the second part is telling there's a Dirac operator behind everything that glues everything together with edges, which I'm not going to say much about because you'll see just getting the nodes themselves under control is it's work. All right. So now I'm not the originator of the results here. So the project I picked up is they did their work, and you'll see how things get under, the numbers get out of control quickly. So there's a need for someone to come in and duplicate all the numbers, preferably with different methods, which is what I was fortunately able to do. The original work, okay, so this is work of Gates, Hu, and Mack. It's either 3 or 4 papers, depending on how much you want to get into things. And what's in their results, we're going to have these Adinkra with a Y diagrams. There's going to be either 1 or 2 for each orthogonal group. SONs going from 4 to 11. 4 to 11 are going to be where the ones that are important to string theory and supersymmetry are. So they're not looking for a general result that tells you how to do all these decompositions, although there are certainly people who do those type of things. Their methodology is based on Young diagrams, which I'm not going to talk about, but Rishi actually has a student who's managed to push some of the results in that they were doing forward. And a feature of what they're doing, it's very computer intensive, and Mathematica seems to be the program you want to use. The CUNYRT program is where you go for tensor procs. That seems to be the state of the art for doing tensor procs these days. Great. And so let's talk about what their results actually look like. And so you're right. And so what we're doing is validating the diagram. So the idea is the diagram has nodes, it has edges. You'll see that these numbers, like you just start generating long lists of things that you need someone else to go through and come across in a different method. All right. So I showed you the SO4 diagram. What do we have? So what you're going to do is you take the spin rep. S is going to be either a spin or a sum of 2 spins. We're going to form the exterior algebra. That's going to still have a representation of your SON, so I can decompose that into irreducibles. We have full reducibility, so that's not a problem. For each level in the diagram, that's just going to correspond to degree K. We decompose, and then each node is going to correspond to one of these irreducibles, possibly with multiplicities. Okay. For the links, so I don't mention where it comes from the physics, but the idea is if I'm at level 10, I want to go to level K plus 1. What do? We tensor with the basic spin rep. That's going to get you not back into the alternating part of it. It's going to just give you a whole bunch of irreducibles. Some of them will go alternating, some won't. But we put a link to anything that can possibly show up. So we're not going for the precise picture. We're just going for possibilities with the links. Because of course, if you're going to go for the precise picture, you have to calculate the vector level, which is probably unreasonable for some of the sizes of things we're doing. Okay, and so that's kind of generally how we put things together. All right, for examples, this is the SO4 from the page I showed you before. Okay, so things you'll note here, the nodes alternate between black and white, so that's bosons and fermions. We have labels, which are going to be highest weights for representations. I'll say something a little bit about Dinkin labels. So I'm sure everyone here loves root systems and the labeling that comes from root systems. For doing computer science or programming, you actually don't want to use that at all because you don't want negative signs in your work for labeling, and you don't want halves in your work for labeling if you're using spin. So going to Dinkin labels actually makes life a lot easier. For the 6-dimensional, this one's generated by 2 irreducibles. So actually it's generated by the spin, but the irreducibles for the SO6 are going to be the 2 half spins. So you're really just using the 2 half spins in level 1. All right, and that one has colors because for the tensoring, you can also keep track of which irreducible you're tensoring with. The one I like this one. The other ones are nice. I like this one. This one you can kind of stare at for a little bit and try to unfold it and see if you can get it to any of your favorite Hasse diagrams that show up in, you know, like Bruhat ordering or things like that. And this one does wind up being related to, I think the E8 ordering.
The n equals 1, that means they weren't supercharged, or?
One dimensional, meaning I think, yes, one supercharged, right. Right, so that's your D operator. Okay. Yeah, I don't want to swear to that. So right now I'm running through my head what n equals 2 is doing.
Okay.
All right, so that's the problem. I want to take an exterior algebra over a spin, decompose. So I showed you SO4, SO6, and SO10. They're very reasonable. You don't need a whole lot of computer fire. You need the LeArt program, but you can do everything pretty much by hand in Excel, like no problem. When we get to SO11, which is pretty much at the peak of what we want, when you start counting the spin rep, okay, well, SO11, that's 2 times 5 plus 1, so the spin rep has dimension 2 to the 5th, 32. I take the exterior algebra over that, that's going to be 2 to the 32, which means I want to decompose space with dimension just over 4 billion, okay, which is, you know, probably not something we do every day. Even as an actuary, we don't do things that big. At the end of the work, okay, the number of nodes you wind up in your diagram it's 2,500 about. And even in the middle level, so if you go by degree, the biggest piece is degree 16, and that's 600 million dimension. When you break that down, the largest piece is dimension 31 million. So things here are pretty unreasonable. You don't want to deal with the vectors directly if you can. Even dealing with character formulas, things are hairy, I guess. Okay, so this is what the output looks like for the wedge 16. I'll say more about Dinkin labels in a little bit. So this has 296 components in the middle. Let's see what things to note. The way the list goes, so this is what it looks like in the Gates, Hugh, and Mac papers. These are the things you want to verify, these lists. What do we have here? So in blue, you have these 5-digit strings. These are your Dinkin labels. And preceding each one of those, we have a number, which is the multiplicity that shows up in the decomposition. So this one is where a lot of the work is, because those 296 irreducible components, that's where these 200 some tablers are going to come from just for this one case. Okay, so how do you do this? If you're not going to use Young diagrams, well, one way to do this is to, well, kind of, if I'm not thinking specifically about orthogonal groups or general linear groups, one way I can go is just to think about the weight space and try to peel off irreducibles, one irreducible at a time. And that's pretty much how we do this. For the things up to 10, that's completely reasonable. That's just, you know, you do a little bit every day and you get done. For the 11, though, like kind of like no regrets going up to 10, and then 11. Maybe I'm thinking maybe I should have just programmed this directly in there. But good for having not done actuarial work in a long time. Good to get it to use in a project. Now, so for the validation, what I want to do is we want to take a look at the dominant weight sets. I'll remind you what dominance is in a little bit. 3 parts that I need here. I'm going to need to get the dominant weight set for the level that I'm working in of the different SON. I'm going to need the irreducibles that I can extract from that. And then I'm going to also need to do the decomposition in some environment, which would be perfect for Excel. So we're going to have a table. I'm going to have a whole bunch of auxiliary tables for the irreducibles. And then I got to figure out a nice way just to make all this flow that peels off everything one at a time and records it. And I'll show you how that goes at the end. Now, to review things, okay, so we don't want to start off and talk about spin groups and all that. All I need here is the theory of the weights for spin. And even then, it all kind of just gets dumped into the computer. Let's say we do SO odd, so the type Bn. Then what do you have for roots? You've got long and short roots here. You have positive roots. You've got your simple roots. So these are all the natural choices. And then I'm going to want to one way to represent the weights is with tuples in a natural way. And so if I do that for the spin rep, the weights are just going to be 1/2, and then you got your plus minus ones in each coordinate, which is harking back to binary codes. And so like, if there were more time, I would be more precise about that, but that's where you see the connection to the first talk, is through the spin rep. Other things that are going to be important here. And so the idea, like I said, you don't want to work in a root basis. So you need to just get to the idea of dominant weights as sums of fundamental weights. So what do we get when we choose a positive ordering from the previous page? You've got your ordering, you've got fundamental weights. So this is going to be a basis for the full weight space. Dominant weights are then just sums of fundamental weights. And then I can turn any weight into a Adinkra label by just taking the coordinates from the fundamental weights. And then if I'm talking about a dominant weight, it's very convenient that your tuple in terms of fundamental weights is just going to be a list of non-negative integers. So you don't have to worry about the 1/2, you don't have to worry about the negatives. And for the numbers we're working with, you never go double digits either. So this is like perfectly in the range that you want for doing a problem like this, for labeling hundreds of things. All right. Note the way we label our irreducibles is just going to be with highest weights, but I'm going to use highest weights given by Adinkra labels. Okay, so I think we all have this. And in Mathematica, okay, so this is what it looks like when you run the code in Mathematica. There's no no top-down programming going on here. It's literally 2 or 3 lines of code right through the command line to get you your tables that you want. You export them right out to Excel, and then you can go about your business in Excel. The 2 things you need for this project, you need to calculate dimensions. So the big piece that I mentioned earlier, its Adinkra label is 21012. You see the 31 million come out there. And then if you want the table that goes with that, so the weights and multiplicities, this will go down far past what I have on the board, but I just wanted to show what it looks like in Mathematica. All right, and so and the thing to note too, one thing with Mathematica, when you do tensor product decompositions, you can put the command in there, but there's no guarantee that you're getting a result back in a reasonable amount of time. Here, even for the biggest piece, you get the weight table out in under a minute. So this is a thing also where you're not sitting waiting for the machine. You can crank out these weight tables as fast as you need. And the time load on the project comes from putting it all together. Although this is something too, you could just program and let the computer do it if you want to do it top down. All right, so how do we get the dominant weights for the exterior product? Well, for that, we're pretty much going to just go to characters, and then there's a nice formula, which really you could go to, well, I'll show you. So the action of SON on any wedge, well, what do? You're just going to use Leibniz rule, hit 1 coordinate at a time. If we're doing weights, that says to just add up the weight for each coordinate, and that's going to give you the new weight. Now, also note, since I'm using exterior algebra on a basis or whatever, I'm not allowed to duplicate weights in the weight set. And by that, I mean, you're not allowed to duplicate the indices if you list them. So you could have 2 weights that are the same, but you're not allowed to do them for the same weight vector. So they have to be distinct. The way we get these conveniently is just loading things up into a character. Okay, so of course, character for this is just the trace of the representation, which turns out to be take our variable for the weight, I put the weight in the exponent, put the multiplicity out in front, and then the formula that I use to capture the characters of all of my levels at once is just given by this familiar formula here from combinatorics. And one thing I'll do is I'll tune up this with a z to keep the levels separate. So each power of z is going to give you your character based on what level you want to work with. Of course, you could do this directly just using elementary symmetric functions, but you get the whole thing in one shot if you do it there. All right. And then as noted, once you have the dominant weight set for the level that you're interested in, what do? You identify the largest weight in there. You go to your table for that irreducible. You extract all those weights out, including the multiplicities, and then you record, and then you keep repeating until you run out of everything. And then that's the algorithm. Finally, how does this look in Excel? So this is the sheet for, so it's like I try to do the 16, which is the biggest one, but since it's hundreds of tables in Excel, if you kind of blow it up to try to get the whole thing in there, you get no resolution at all. And then if you go too close, it just looks like a big mass of stuff where you can't really separate anything. So going for the 16, you can't get a sense of the scale, or you can't get the details and the scale at the same time. So for wedge 2, for the SO11, well, that's reasonable enough where you can wrap your head around the whole thing if you're seeing it for the first time. So this is what the output looks like. What's happening here, for the wedge 2, you're going to get 3 components. I'll tell you what each part is. For the exterior algebra, for wedge 2, in the box, what we have is the list of dominant weights. It's in reverse order, so the highest weight is at the bottom. We have the column on the right, which gives us the multiplicities. And the goal is going to be to match out those multiplicities. So that's the first box is our exterior algebra character. What I'll want next, well, the things that are in the exterior algebra are the only weights we actually need to consider. They're not, irreducibles are not going to produce anything outside of that. So I'll just start at the bottom and start peeling the irreducibles off as I go up. And when you do that, in the far right box, what we'll have, in green, we'll have the highest weights. We'll have the multiplicities that come from Mathematica underneath. And then if I add across, and really, it's not just adding across because you want to make sure you put multiplicities in there if they occur. That has to add up to the purple table on the left. And so that's not just getting your decomposition, it's cross-checking at every weight. So you can't just get, well, you wouldn't just want the highest weights to show up. You have to have all the weights matching up also. And so if they didn't match, you'd have to go and troubleshoot. And that's the decomposition. We have another cross check, which will be by the dimensions. And so up above, so I'm using the same highest weights in green, but above we're going to put the dimension, the multiplicity. I can multiply, add up. That'll give me the dimension of the level of the exterior algebra that we're in, the wedge 2. But we can calculate that also with 32 choose k in this case. That's how you calculate dimensions of levels in the exterior algebra. And so that's going to be our last cross check on this thing. And then that's the Excel model for finding the nodes in an Adinkra in the validation. So that's a talk.
Great. Thank you, Paul. Are there any questions? And including people from chat or from the Zoom, rather, I can also read your questions if you have any. But any questions at all? From the audience or from Zoom?